Hello everyone. So today I will, in the first part, I will briefly touch upon the two methods that has been discussed for finding the gradients, which is very important for calculating the secondary gradient terms in an unstructured mesh in the problem where we solve for a steady diffusion equation. Okay. So as you know, gradients of the dependent variable might be needed in for different reasons. So one of them is getting the computing the secondary gradients. Also there are many other quantities like secondary gradients, and also in the Navier-Stokes equation, that is the equation that governs fluid flow, we require to compute the gradient of pressure. Okay, so in the momentum conservation equation we have the gradient of pressure, we need that. And also if we have some non-Newtonian fluid, where the viscosity is dependent upon the gradient of velocity, in these cases also we require to compute the gradient. And overall in turbulent CFD computations for say some turbulence models and turbulence models, we require to create different gradient terms of different quantities, which allows us to model the terms in the turbulent kinetic energy or turbulence models, right. For example, in the K epsilon model, or even in a large eddy simulations, we require the computation of gradient of the velocity field, which in turns helps us to compute the turbulent viscosity and so on, right. So just to give a motivation of why we require a method to compute the gradients of the dependent variables. Now there are actually two well established methods for calculating the gradients of the dependent variable. So one of them is called the gradient theorem approach. Also called the Green-Gauss approach. And there is another method called the least square method that I will briefly brush upon in the next part. So to start off, so the gradient theorem utilizes the Gauss divergence theorem that we had used while discretizing the diffusion equation, the steady and unsteady diffusion equations, where we converted a volume integral into a surface integral by converting the divergence term inside that. Yeah. So for example, if you remember, if we have a control volume integration of a gradient of a field, so we can write it like a surface integral, right. Control surface integral, and this dV will be converted to a area, and we can just to further discretize it, we can just write it as the summation over all the faces, right. So phi f and af, right. So where can we use such a thing? For example, we can, in a discrete form, this integral, this volume integral, we can write it as like this, right. So the gradient of phi times the delta v. Okay. So and this will be equal to the summation over all the faces and the value of phi at the different faces and the area of the face, right. and the phase value will be the cell centroid value, sorry, not the cell centroid, the phase centroid value, and you can use different interpolations to get the value of the dependent variable at the phase, right. Now how do we compute the phase center value, right? For example, if we have a grid system like this, for example, one cell here, yeah, so one cell here, another one here, let's write it as C0 and C1. So and we have the area vector in this direction. So we want the value at the phase center, right? So this is the value we are interested in, and let this vector delta r naught bar, let this be the vector which connects the cell center C0 and the phase center. Let's write it as F. Okay, let's not write it as F. Okay, and let this vector delta r1 bar be the vector connecting the cell center C1 and the phase center. Okay, now we can first make a basic assumption. So we'll assume that we are agnostic of the fact that the delta r0 and delta r1 might be different for both the cells. We just assume that they are both equidistant, the cell centers are equidistant from the phase center, and we can just take an average of the two cell centers, right, phi naught plus phi 1 by 2. Just take a simple average. Later on we will go on and refine this approximation, right. So now let's write the term the phi f in terms of the two cell centers using the Taylor series approximation, right. So in Taylor series in one dimension, if you remember, it was just very simple, phi f naught phi no, so we are trying to get the value of phi f yes, we are trying to get the value of phi f from, and we are trying to reach the value of phi f from phi naught from cell center C naught. So we, in one dimension it is quite simple, it's phi naught times delta x and higher order terms, but we will write it in a much more general sense. We can just write it something like this: phi f is equal to phi naught times gradient of phi, this is just a vector, and times the delta which, okay, so this will be delta r naught, right, because delta r naught is connecting the cell center C naught and the phase center. So delta r naught bar plus the higher order terms, and similarly we can expand, we can reach the value phi f from phi 1 also. So in that case everything will be same, but instead of r naught it will be r1 bar, right, because this vector is responsible for connecting the cell center C1 and the phase center. Let me just write it properly. Okay, and this gradients will be computed at the cell centers. Okay, so we have the value here. Now what can we do is that we can just add these two equations, right. So let this be equation 1 and equation 2. We can just add 1 and 2, and what we will get in the left hand side is 2 phi f, right, and we just divide it by 2 in the right hand side. So we can just write phi f equal to half of phi naught plus gradient of phi at C naught delta R naught. We will just ignore the higher order terms, phi 1 plus the gradient of phi at 1 and times delta R1. Okay, so now that we have this form, what we can do is that we can replace the phi f in the, so here the phi f we got the value of phi f as a representation of this. We can just plug the same thing in this equation, right? If we plug the same thing in this equation, sorry, not this one, yes, in this equation, right? So now that we have done the Taylor series expansion, and we get another expression for phi f, which is also in terms of gradient of phi and gradient of at both the cell centers. So we just plug it in here, right? Because and with the new updated phi f values, we can just again get another approximation for gradient of phi, right? So just to give a overview of the problem. So if so first we started with a control volume integral delta v equal to, it was as control surface, sorry, it was converted into a surface integral of phi dA, and the discrete form was something like this, right? Phi at all the cell centers, right, at 0, 1 and 2 whatever, and times the volume is nothing but summation over all the faces of phi f and AF, right? And we get an approximate value of gradient of the gradient of phi as this, right? So phi f AF 1 by delta v, and initially we compute the phi f just by some average. So we just use this simple assumption and get the value of phi f. Now also then we as I have shown before, we will just do the Taylor series expansion here, and we will just add both these two equations and get an expression for phi f, right? So we get an expression for phi f, which is nothing but half of phi naught plus gradient of phi at delta R naught plus phi 1 plus gradient of phi at 1 delta R1, right? And now since we have already an approximate value of the gradient of phi, so these terms are all known to us, right? These terms are all known to us. Even for the mesh, we really do know what the these R naught and R1 vectors are, and also we know the phi naught and phi 1. So then we get another approximation of phi f, right? Then we again go back to the top equation that is shown here. So with this new approximation of phi f, we again plug in the phi f in this equation. So gradient of phi at the cell centers, I am writing CC, and so phi 1 and phi naught are known from the previous time step, right? No, phi naught and phi 1 are both known. So these are not representative of time steps. So phi 1 is just the value of phi at C naught, and phi 1 is just the value of phi at C1. Okay. So these are all known values from these known values we need to compute the gradient. So, for a structured mesh and uniform mesh, this is quite simple. So, this is just a method how to get it for an unstructured mesh. Okay. So, yeah, so just to give a brief overview. So, what we did was that we compute the gradients using some approximate phase center values, which we get it from this expression, and then we get a approximate value for the gradient of phi. Then we use this approximate value of gradient of phi to get the phase center values phi f using this expression. Then we get another a better approximation of phi f. We then go back to the previous equation, and we do, generally it takes 2 to 3 iterations to get a converged result, right. So, this is one method. So, if anyone has any doubt, please tell me. I'll try to explain again. Okay. Okay, so it's quite simple, I guess. First we get an approximate gradient of phi value, then we do use this value to compute the phase center phi values, and with those new phase center phi values we again get back another approximation for gradient of phi, and we just do a 2 or 3 iterations like this, and we'll get a quite converged result, right. So, the more non-orthogonal the mesh will be, the longer it will take to arrive at this kind of solutions, right, because at that time the gradients in the face normal direction will have a more effect as compared to a mesh which is orthogonal, and orthogonal. Uniformity does not play any major role in that. Okay. So, now coming to the second approach, it is called least squared approach, right. So, you might be familiar with the least squared approach, where we have, for example, a two variable system, one dependent, one and independent, say maybe x and y, and we get some data points from experiments, right. So, something like this, and we want to fit a line, we want to do a linear fitting of these points, and we just assume that this line is the best approximation of how y is varying with x. So, how do we get this? We just what we try to do is that this line might not be passing through any of the points that you get from the experiment, but it will at a in a least square sense, it will have the least errors between the distance. So, we just compute the distance from each of these points to the line, and we try to minimize this distance as much as possible. So, this is a similar approach that we take here to also to compute the gradients. Okay. So, let me just construct a mesh, 2D mesh to demonstrate how it works. So, this is a cell in the mesh, let us write it C0, and it is surrounded by 5 neighbors. So, C1, C2, C3, C4 and C5. Okay. And from each of these from the cell center C0, we can draw n number of vectors pointing towards the different cell center different cell centers of the neighboring cells, right. So, for example, we can have a vector pointing this way, which is nothing but R1, this one will be R2, right, and similarly we will have the number of neighbors we will have the same number of vectors also, delta R 5, right. Now, again what we will do is, again we will use our very handy tool, the Taylor series expansion, and we will express each of the neighboring cell center values in terms of the C naught cell center value, right. So, we will write something like this: phi 1 is nothing but phi naught plus gradient of phi at C naught times R1, right, and some higher order terms we will just neglect them. Similarly, phi 2 is phi naught plus gradient of phi naught, not gradient of phi naught, means gradient of phi at C naught, let us write it something like this, times delta R2. And similarly, we will have, for example, if you have m neighbors, so for m neighbors we will have some m number of equations like this, right. Okay. So, now that we have this, let us see what let us break down this term and see what can we make out of it. So, what will be the gradient of phi at C naught? It will be nothing but I cap dou phi dou x at C naught plus j cap dou phi by dou y at C naught, right. And what will be the R I or maybe R1, R2, R3? Let us write it in a generic form. So, R I vector will be, what it will be? It will be just the x component and the y component, that is nothing but for example, if this coordinate is x naught and y naught and this is x1 and y1, this R1 vector will be nothing but x1 minus x naught I cap plus y1 minus y naught j cap, right. And in general term for Ri, it will be nothing but xi minus x naught I cap plus yi minus y naught j cap, right. Or we can just simply write something like delta xi I cap plus delta yi j cap. Okay. Yeah. So, now that we have these terms, let us write it like this, let us write it here, delta xi I cap plus delta yi j cap. Okay. So, what will this term be? This is nothing but a dot product, right. So, I cap will be get multiplied with I cap, j cap with j cap. So, what do we have finally? We can write gradient of phi naught delta Ri, let us write delta Ri is nothing but delta xi dou phi dou x at C naught plus delta yi dou phi dou y at C naught. Okay. So now that we have this form, we can represent it in a matrix form also, right? So let's try to represent it in a matrix form. So these are the equations, right? So we have m sets of equation. We'll just take the phi naught phi naught in the left hand side and we'll rearrange the terms, right? So this is the term in the left hand side. Let's write so it will be what, delta x1 dou phi dou x naught, or let's simplify it more. We'll just denote dou phi dou x as phi sub x and dou phi dou y as phi sub y. Okay, it just makes our life simpler. So this term we can write it as what? So for the first equation, that is this equation, what we can write, this is delta r1, right? So it will be delta x1 phi x plus delta y1 phi y is equal to phi 1 minus phi naught, right? Because we have taken the phi naught in the this side. Similarly, for the all the other m equations, we can write something like this. Okay. So what are the unknowns here right now? So we only have two unknowns here, right? Phi x, phi sub x and phi sub y, that is the gradients, dou phi dou x and dou phi dou y, right? These are the unknowns. And what are the known values? We very well know the delta x1, delta x2 and all these things, right? We all we know these things because these are just the distance between the two cells in the x and y direction, between the cell in consideration and the cell and its neighbors. And these values are also known to us. These are coming from the previous time step values. Now that we have this, we can just rearrange it in a matrix form, right? So this part will term it, will keep it in the right hand side. So we'll try to arrange it in a ax is equal to b type of formulation, where what will be the a? So a will be nothing but delta x1, delta y1, delta x2, delta y2, all the way to delta xm, delta ym, right? And what will be our the vector which contains the unknowns? It will be nothing but phi x at c naught and phi y at c naught, that is the gradients. And the right hand term will be nothing but these known values, phi 1 minus phi naught, phi 2 minus phi naught, and so on, phi m minus phi naught. Okay. So now that you have this equation, so if we have m number of rows and 2 columns, so this will be of an m cross 2 matrix, right? And this will have only 2 rows and 1 column. So this is just a column, just a vector, and this will be also m cross 1, right? And yeah, it seems to hold hold up, because m cross 2 matrix multiplied by a 2 cross 1 vector will give us a m cross 1 vector as well. Now, what is the problem here? The problem here is we can't invert this matrix, right? It's not we cannot invert this matrix, and also this is sort of an overdetermined system. So, we have, what do we have here? We have m equations, but only 2 unknowns, right? And this results in a overdetermined system. So, now how can we get the gradient values, right? So, if you remember, in the beginning of this section, I had told you about the fitting problem, that we had some experimental values which are like some values like this, and we want to fit a line which has the least squared error. So, the error will be squared, and in the squared sense the error should be minimum, that is, the distance between the points and the line should be minimum. So, it sort of becomes a sort of a problem where you need to get the residuals or the errors between the points and the line to be minimum in a squared sense. Okay. So, let us now define how can we write the residuals. So, what is the residual, right? So, residual is nothing but, for example, if you have this equation, let us take, let us write it in gradient terms, it will be easier. This was the equation, right? Yeah. So, so these are the variables, right? So, these we need to find this. Let us term it as A and let us term it as B, right. So, delta x1 A plus delta y1 B equal to phi 1 minus phi naught, and we want the values of A and B such that the residual will be the minimum. So, what is the residual? The residual is defined as, so for equation number j, we can just write it as R j as delta x j times A plus delta y j times B minus of phi j minus phi naught. Okay. So, for each of the m equations, we will have m equation of residuals, and we want the residuals in a to go to a minimum value for our target or the unknown value of A and B, right. So, the total residual, what can we write? So, this is for one cell, right. You will always remember. So, we are only concentrated in one cell right now. We are not looking at the broader or the global picture. We are just concentrated on one cell with which has m number of neighbors. So, the total residual let us write it as capital R, is nothing but the summation over j is equal to 1 to m summation over all the rj's, right. and what is this actually? So capital R is nothing but summation of j equal to 1 to m delta x1a plus delta y1b minus this will be j, right? Phi j minus phi naught. Okay. So this is the value, and we want to minimize it in a squared sense, right? So what we have to do is that we will square the residuals at each for each of the neighbors, and this will just become a squared term, right? So in a so the residual in a squared sense should be minimum. So this is our residual that we have created, and what will be the minimum at the minimum value? What will be one of the parameters that we generally search for, right? So how do we find the minimum of a certain function? So in your class 11th and 12th, I think you have in calculus for to find the minimum value, we find the gradient, and we set the gradient to 0, right? We set the gradient to 0, and wherever the gradient goes to 0, we say that the function is either a maximum or the minimum value, right? So in this case, we will only concentrate in the minimum value, right? So for example, if a function, just to recapitulate, so if a function goes like this, and at this point, this is the minimum value, right? So let this be y, let this be x. So what is the gradient here? At this point, it will be something like this, which is some sort of a positive in a positive gradient. So tan alpha. So tan alpha is acute, so it is some positive value. As we go in this part, the alpha angle becomes obtuse, so it becomes a negative value, but somewhere in between this positive and negative value, it has to go to 0, right? So this is the point. This is the point where it goes to 0. So here, if you compute the gradient, the alpha will be nothing but alpha will be 0, and tan alpha is also 0. So yeah, so just to give you a brief recap on the minima and maxima finding, the same is true for maxima also, right? So if a function is there, for example, something like this, in this part we will have some positive gradient, in this part some negative gradient. So from positive to negative, we will have a transition point where the gradient will become 0, and that is nothing but this point, which is the maximum value here, right? And after we set the gradient to 0, we again did the second derivative and third derivative to further quantify whether this is a minima or a maxima, right? So but here we do not need such analysis, and we do not need to go to higher derivatives. So what are the dependent variables here? What are the unknowns here? So a and b, right? So for a and b, what we will do is that we will take the gradient of r with respect to a and gradient of r with respect to b. So we have dou r by dou a is nothing but j equal to 1 from 1 to m. This is 2 times, so this will become 2 times delta x j a plus delta y j b minus phi j plus phi naught, and then all of these are not a function of, does not contain a. So all these terms will when we apply the derivative, this will all go to 0, only this term will survive, delta x j will survive, and dou a by dou a is nothing but 1. So we are left with this delta x j, and this should be 0. Similarly, another we have another variable, right, b, another unknown. So taking the gradient along b, we will have 2 times delta xj a plus delta yj b minus phi j plus phi naught times delta yj equal to 0, right. So, now from m equations we have reduced our number of equations to 2 equations here. So, we will just these terms will get cancelled, and what will be the equation? Let us write it as equation A. Okay, we will get confused. Let us write it as equation alpha and equation beta, right. Now, what we will do is just we will expand this alpha equation and beta equation and see how it looks like. Hi Deepraj, you have any question, or you can just mute yourself if no question is there. Okay, so equation alpha. Hi Deepraj, if you don't have any question, can you just mute yourself? Some sound is coming from the background. Okay. Okay, so equation alpha, we'll just write it down. It is summation of j is equal to 1 to m, then delta x j a plus. Okay, so we'll just take it inside delta x j square, right? Delta x j square times a plus delta y j delta x j times b minus of phi j, sorry, minus phi naught times delta x j. Okay, and remember it is a summation, and so if we just expand the summation, it will look something like this. So this will look like delta x1 square a plus delta y1 delta x1 b plus phi 1 minus phi naught delta x1. This is for 1. This is like delta x2 squared a plus delta y2 delta x2 b minus all these terms, right. So and also let's write equation b as well. So equation beta, can be written something like delta x1 delta y1 a plus delta y1 square b minus phi 1 minus phi naught delta y1 plus delta x2 delta y2 times a plus delta y2 square b minus all these things, right. So now we will try to create a different matrix to solve, right. So what do I mean by a different matrix to solve? So here if you look at the A matrix that we have created, for example, where we, yeah, this matrix, right. So the A matrix that we had created before, where we had a over resolved system. delta x1, delta y1 and all these things. Let's write it here. Okay, so we have this, and what is this? This is m cross 2, right? And if we take the transpose of it, so if it is A, so A belongs to this m cross 2. Just don't okay, I'll just not write in this term. So A is a m cross 2 matrix, right? And what will be A transpose B? A transpose B will be a 2 cross m, right? So the transpose, what we do is we just flip the axis, right? So the x axis becomes the y axis, and the vice versa. So the number of rows becomes number of columns. We replace the number of columns to a number of rows. So the A transpose matrix, how will it look like? It will look like something like this: delta x1, delta x2 and all these things, and delta y1, delta y2 and all these things, right? So now if you want a system of for example, we started with two variables and not two variables, two unknowns, and m equations, right? So now we saw that this is sort of a hard task to get the solution to this system. So we later want to do, we want to cast this problem in terms of minimizing the square of the total residual, and we want to convert it into a two unknown and two equation system, right? But for that we need to convert this m cross 2 matrix into a 2 cross 2 matrix. So here from A and A transpose, we can see that we can we use these two things, right? So if we multiply A transpose by A, so that is nothing but a 2 cross m matrix times a m cross 2 matrix. This will give us a 2 cross 2 matrix, right? So let's just write the two A transpose and the A matrix, and see after multiplying what comes up. So delta x1, delta x2 and so on, delta y1, delta y2 and so on. And what do we have? We have here delta x1, delta y1, delta x2, delta y2, like this, right? So if you multiply this, what it will be? It will be x1 times x1, x2 times x2, x3 times x3, this, right? So the first, so this will result in a 2 cross 2 matrix, right? So this is the matrix. So let this be B11, B12, B21 and B22. These are the four elements in the matrix, and we have just denoted it as this one, right? So what will the B11 term be? This will be nothing but the inner product of this vector x1, x2, x3 with the same thing, right? So B11 will be what? Delta x1 squared plus delta x2 squared plus and so on, plus delta xm squared, right? What will be the B12 term be? So the B12 term will be, this will be this vector multiplied by this vector. So this will be delta x1 delta y1 plus delta x2 delta y2 plus delta xm delta ym. So, does these expressions look similar? These terms actually we found out that these terms appear in the alpha equation, the opened up alpha equation, and the beta we are okay. So, let us leave out beta now. So, we see that these terms come up, right? These terms do actually come up. So, let me just copy it down. Okay. So, now if you see, if we again break it down, so we have delta x1 squared, delta x2 squared, and all these things. So, we can just write them all together, delta x1 squared plus delta x2 squared and so on, plus these terms, right. So, delta y1 delta x1 plus delta y2 delta x2 and so on, right. This will be multiplied by what, by a, and this will be multiplied by what, it's just b, right. And there was a 0, remember, I forgot to write the 0 here, this will be equal to 0. So, now that we see that we have a similar form, so what can we write it as? We can write this part. So, we have some additional terms here, which is nothing but let us write it here, equal to say minus, oh, this is already minus, so it will become plus phi 1 minus phi naught delta x1 plus phi 1 phi 2 minus phi naught delta x2 plus and so on, right. So, what can we write it as? So, this is nothing but B11, right. So, this is nothing but B11 and this is nothing but B12, right. And let us look at this part also. So, in the matrix form of the over determined system, we named it as B, right. So, this matrix as B. So, B matrix was nothing but phi 1 minus phi naught, phi 2 minus phi naught and so on. And what kind of not matrix, what kind of vector it is? This is M cross 1, right. So, now if in the left hand side we have a 2 cross 2 matrix and a 2 cross 1 vector. So, what should be the right hand side be? That should be also be. So, it is a so 2 cross 2 and we are taking multiplying it with a 2 cross 1. So, what do we get? We get a 2 cross 1 vector also in the right hand side. So, but that is M cross 1, this one is M cross 1, right. So, what do we need? We need something like a 2 cross M matrix and multiply with it and we will get a 2 cross 1 vector. So, what is a 2 cross M matrix that we got here? So, the A transpose was a 2 cross M matrix, right. So, let us just check and multiply and see what terms do we get. So, delta x1, delta x2 and so on, delta y1, delta y2 and so on. So, what we will have? So, we will have delta x1 times this one, delta x2 times this one and so on, right. So, if you multiply, so the first row with the whole column in the resultant B vector that we have, the first element, not B, let us write it as B prime. So, in the B prime matrix, the first element will be nothing but delta x1 times phi 1 minus phi naught plus delta x2 times phi 2 minus phi naught plus so on, and the second term will be nothing but delta y1 phi 1 minus phi naught plus delta y2 phi 2 minus phi naught and so on, right. So this is the vector that we get from what, from A transpose times the B matrix. Okay. So now we can have an expression for this. So this is what, this is nothing but the first element of the A transpose B vector that we get. And also now looking at a B21 and B22 term. So B22 term is straightforward, is just y1 square plus y2 squared plus all that things. So let me write it in another. B22 is straightforward, delta y1 whole square plus delta y2 whole square plus so on and so forth. And what about beta 1 2? Beta 1 2 or beta 2 1, this is the same thing, right, because this is nothing but a symmetric matrix. So beta 2 1, beta 1 2 is nothing but this row times this column, right. This is same as the beta 1 2 that we got here, right. And this is nothing but delta x1 delta y1 plus delta x2 delta y2 and so on. And now again looking at the equation beta, what do we get? We get a similar form, right. So equation alpha we found out. Now equation beta, we see we got multiplication of A times delta x1 delta y1 plus delta x2 plus delta times delta y2 plus so on and so forth, plus b times what, b times y1 square y2 squared and so on, b times y1 square plus delta y2 squared and so on. And again we have this phi 1 minus phi naught delta y1 plus phi 1 minus phi naught delta y2 that we already got from this term, right. A transpose times B, delta y1 this one, delta y2 this one. So this part we can write it as A times B 2 1 and this is nothing but B times B 2 2, right. So now in a matrix form, if we write that B 1 1 B 2 2 B 2 B 1 2 B 2 1 and B 2 2, and what do we have multiplied with it? So B 1 1 is multiplied by A and B 1 2 by B. So A and B, and similarly B 2 1 is multiplied with A and B 2 2 is multiplied by B. Okay. Equal to what? Equal to the A transpose B, the first element of that, and A transpose B, the second element of that, right. Now we can again just write it in terms of a matrix vector multiplication, B 1 1 times B 1 1 B 1 2 B 2 1 B 2 2, and this will be our unknown vector. A and B is nothing but A transpose B, or let me just write it down. So delta x1, delta x2, delta y1, delta y2 times what? This will be a m cross 1 vector, which is phi 1 minus phi naught, phi 2 minus phi naught, and so on, right? And what is this this matrix, this B matrix? It is nothing but A transpose A, right? So what can we finally write? We can write the equation as an A transpose A times the gradient vector, the unknown, is A transpose B. Okay. So now we have a what is this? This is a 2 cross 2, 2 cross 1, and a 2 cross 1, right? So now we have two unknowns and two equations, and this kind of system of equations is very straightforward for you to solve, right? So for an unstructured grid with m neighbors, we had initially so also please pay attention that we are writing as two unknowns, right? So in the case that that we have a two dimensional grid, in that case only, specifically to that case, it will be two unknowns. Right, but if we have a 3D mesh, three unknowns, right? And what will they be? They will be nothing but dou phi dou x, dou phi dou y, dou phi dou z, right? And these are all at a particular cell center. Okay, so we have m equations and two unknowns. Then we constructed the residual which is nothing but a summation of all the residuals at all the faces squared. Then what did we do? We got a two equations we got, right? Now we had to formulate this as a system of linear equation problem. So what we did is that we represented it as a matrix form, and by using the relation that at the minimum r we have the gradient, let's not write gradient, the dou r by dou a and dou r by dou b, where a and b are the required gradients, right? So we take the gradients of the residual along those variables a and b, that is the dou phi dou x and dou phi dou y, and we set it to 0. because from calculus we know that at the maximum or the minimum value the gradient goes to 0. Then we get a two equation and two unknown systems, right? A system of equations which has two equations and two unknowns. And remember, this system needs to be solved at each grid point, right? So we have these two equations and two unknowns at each grid points, and only for a 2D problem. So let me just write it here. Only for 2D, right? Because for 3D we will have a 3 equation system. So 3 equations and 3 unknowns. So in this way we solve this what is this the system of linear equation system represented in a matrix form. We can write it as A transpose A times the G equal to A transpose B. This kind of Ax is equal to B solve we need to do for each of the cell centers, and we will get the gradients. And now that we have all the gradients, we can easily compute the secondary gradients as well as all the other pressure gradients and all the velocity gradients that we need to do our further calculation in turbulent flows or unstructured grid. Okay. So this was the method. It seems to a little bit more elegant than the iterative method or the Green-Gauss method that we had explored earlier, right? So any questions regarding this least square method? Please feel free to ask me. Okay, I think then we can carry on. So yeah, I just wanted to explain these two topics. Now I'll briefly again brush up how we solve a convection diffusion equation, right? So initially we have only done steady diffusion and unsteady diffusion, which was nothing but a equilibrium problem, right? Steady diffusion is just an equilibrium problem. We do not need to do time steppings and all that. No dou t dou x, and then in the unsteady diffusion problem part, we introduce you to the different time stepping schemes and how to deal with the temporal integral t plus delta t of some quantity phi dt, right? So how to deal with this kind of integrals. Now so we had seen only the two classes, the steady and unsteady, and only diffusion based problems. Now there is so if you remember the general scalar transport equation, let me just write it down. Rho phi. Okay, let's determine vector notations. Divergence of rho phi u vector diverge del dot gamma grad phi so this is the unsteady part, this is the let's say convection. this is accounting for the diffusion, and this is the source, right. So, initially we had completely neglected the convective part, right. We only focused on the diffusion and the unsteady part and how to deal with the source term, but now we will bring in the yeah. So, now we will bring in the unsteady part, and then see how to discretize a system the governing equations in this diffusion and convection dominated problems, right. So, there is something called advection and diffusion, advection and convection, right. So, these are sometimes meant in a similar term, but there is a little bit difference. So, advection and convection are not sometimes it might refer to as the direction in which the variable is being carried away, but yeah, we can sometimes use it in a interchangeable manner, right. Okay. So, let us now look at a 2D problem where we will have a source term, the diffusion term and the convective part as well, right. And we'll just leave out the we'll just leave out the unsteady term for now and just look at. So, let us construct a 2D domain. Back to our Cartesian well organized meshes. This will make our life simple, but now you know how to go from a structured to an unstructured mesh based on the how we compute the different gradients, and especially how do we compute the secondary gradients, right. So, let this be P, let this be east, west, north and south. We will assume that each of them are spaced by delta y and delta x. Okay. So, now that we have we will just assume that the velocity vector is very known to us. We will assume it is a known quantity, and then we will deal with the different terms differently. Okay. So, now the first step, if you remember, we will just do a volume integral. So, we will do a control volume integral. This term is quite straightforward, right. SP plus, sorry, you can write it as SP phi p plus right, and this diffusion term we are very familiar with. How to deal with this? We will do the Gauss divergence theorem, convert the divergence, we will just remove the divergence operator and we will be left with the gradient vector and the area vector, which will be nothing but summation over all the faces gamma gradient of f at the faces times the dA, right. And for this kind of structured mesh, we will just have for the different faces, right. So, east, west and north and south. So, it is nothing but phi east, then phi east minus phi p by delta x, and the area will be delta y, right. For the west face, it will be negative because again the area vector points in the negative x direction because of that. So phi p minus phi w by delta x delta y, and also for the north face gamma n phi n minus phi p by delta y by delta x minus gamma s phi p minus phi s by delta y times delta x. Okay, so this is quite straightforward, right? Let me just write it in a much more cleaner form. So it is nothing but, what is this? This is the diffusion term phi east delta y by delta x times phi capital east phi p plus gamma west, sorry, it will be negative, right? Delta y times delta x phi p minus phi west plus gamma north delta x by delta y phi n minus phi p minus phi gamma s delta x by delta y phi p minus phi s. Okay, so now we will use a different terminology. We will just refer to this term as d east. There is nothing but the diffusion term at the east face, d west, d north, d south, right? So what will be our diffusion term looking like? It will looking like d east phi east minus phi p plus, sorry, okay, we can just write it right, dw phi p minus phi w. These are all small small letters, right? Because this is for the faces and capitals are for the cell centers, remember that. dn phi n minus phi p minus ds phi p minus phi s, right? So we have our diffusion term and the source term ready, right? Now we are only worried about how do we get the how do we discretize the convection, the convective part. Okay, so what does our convective part look like? It is nothing but a volume integral Cv del dot rho phi u vector, right, and dv. Now again using Gauss divergence theorem we convert this into a control surface integral and then do a summation over all the faces, nothing but rho phi u vector at face and a vector. All right. Now in our 2D case what is the u vector look like? It is nothing but ui cap plus vj cap, right? It's just a velocity vector. And what is our a vector for the different phases? So a east is nothing but delta y I cap, a west is right, it's delta x j cap, and a south. Okay, Now, if we just break down the summation part, what are we left with? We will have rho phi at east, and for our case this will be u times u east. So, this will be at the face, right. The u's will be, and the u's and the velocities will be different at different faces. We assume that we know that. Let's not go into details how the u is coming. We'll see later when we solve for the actual the proper Navier-Stokes equation, how do we get the u value, which is also a dependent variable in that case. So, for now we'll assume that it is u face is known. So, in the east face this will only be u east times delta y, and I cap will get cancelled, right. So, u e and delta y. Now, whatever the west face, it will be rho, let us write e only, because the rho also might vary dependent on phi, right. So, the rho can also be a function of phi or time, or say whatever. So, rho w, phi w, u w and delta y. Now, for the north face, only the j cap will survive. So, v n delta x minus rho s v s v s delta x. Now, if we look at this term rho times u times delta y, it is nothing but the mass flux, right. It is nothing but the mass flux through that phase. So, rho u a, this is delta y is a, is what at a certain phase is nothing but mass flux to the phase, right. And this is also dimensionally also makes sense. This is kg per meter cube, velocity is meter per seconds, area is meter square, right. So, we have what we are left with, the unit is kg per second, that is the amount of mass that is entering through the phase, entering or leaving depending on the signs that you have. And what we will do is that we will denote it as something called f, for example capital F, small f, that is the convective sort of a convective coefficient, as like we had described the d term in the diffusion term. Similarly, we will define something called f in the convective part also. Okay, just give me 5 minutes. I'll be back. Okay, let's get back. Yeah, so what we had done is so we somehow converted this volume integral to a surface integral. Then in the discrete form, the integral was written in terms of a summation over all the phases, right? Now we define this mass flux term at each phase as F, capital F, and this whole discretized convection term, we can write it like this. So F E V E make sure you have the correct indices. This is will be small n, right, because this is for the phase values, and Fs small s, V small s, right. So now we have all the terms discretized. Let's bring out the diffusion term also. This will be equal to the diffusion term plus the source term, right? Sp Vp plus Sc times delta V, the volume. So in this case, it is the delta V is nothing but delta X delta Y for the 2D case, right? Now we'll try to formulate a sort of a form that we have been working on for so long, for the AP Vp equal to summation A and B Phi and B sort of a form, right, that we had for the diffusion equation, steady diffusion, unsteady diffusion, both the sort of problems that we dealt with. So now, but before that, these values, the phase center values of phi, the east, west, and north and south, we do not know the values at the phases, right? We only know the values at the cell centers, the capital E, capital W, capital P, capital N, and capital S. So how do we get these phase center values? So one simple approximation is we will take the average of the two neighboring cells. This way we can get one get sort of a approximation of the phase at the cell centers, at the phase centers. There are multiple other ways that that we can apply. There is something called upwinding or downwinding. These will be covered later in the course. So we'll stick to the basic sort of approximation, that is nothing but the average of the two cell center values, right? And yeah, so so here we had done a linear approximation, right? Linear that the phi varies between two cells in a linear manner, and here we will take an average approximation, that the phase center values is nothing but the average of the two cell center values that the phase is sharing. So for example, if you have the cell east cell and you have the point P and point capital E, we can write the phi small e as a average of these two points, right? All right. So in this way we can get an approximate, not approximate, we can denote the phase center values in terms of cell center values. Okay. So till now, any question? I hope it is clear to you. Thank you. Okay, so let's now put back the values that we have. So we have f small e. Okay, let me write it this way, by 2 equal to okay. So now let's club all the similar phi terms together and write it down again. So we'll take phi p. So phi p will take it in the left hand side. What will be the phi p value? For phi p we'll have this will come dE plus Fe by 2, right? Now here this is also negative, so dW, but here if you see it is minus Fw by 2 small n plus F small n by 2 d south minus F south by 2, right, because F south is negative, plus the source term is, sorry, this will be minus, right? SP delta V, right, is come from this term. Now what about the phi east term, right? So phi east will have what terms? Phi east has dE and phi east has Fe by 2. This is positive, right, and it will come in the right hand side, so it will become minus Fe by 2 plus phi W, phi capital W, negative negative positive, it will be dW, and this is also negative, so it will become positive, so F small w by 2. And similarly if we do for the other grid points, we will find something like this. Yes, everything is done. The only thing is this SC plus SC times delta V. So now unlike in the diffusion equation that we saw, these, if we define this term as A capital E, A capital W, A capital North, A capital South, the AP is not the summation of the neighboring A and B minus SP delta V. right? Here it's not the same thing, right? If you see, the signs are flipped. So to deal with that, we will just add and subtract some phase mass fluxes to get the AE, AW and all these things. So in here, what do we need? We need to subtract Fe, and as a consequence we have to also add Fe to maintain the net addition 0. So let's write it down. Vp dE plus Fe by 2 minus Fe plus Fe Similarly, in this way we just have to add Fw and we have to subtract Fw as a consequence. D small w plus, sorry, okay, and this will in turn become Vp times dE minus Fe by 2 plus dW plus Fw by 2 d small n minus f small n by 2 d south plus f south by 2 plus Sc delta V, and all these terms, right, all the residual terms from here, which is nothing but Fe plus Fn minus Fw minus f south, right. So now we can finally write it like we want, not fully but yeah, a little bit. So we can write a modified AP. So say AP prime Vp summation of neighbor A and B V and B plus Sc delta V. Here neighbor denotes to east, west, north and south, right. But what is AP prime? It is nothing but summation of A and B, sorry, summation over NB neighboring points A and B plus SP, this is SP, right, SP delta V plus the net mass flux, this is Fe plus F small n minus Fw minus Fs. So what does this term actually mean? So this is nothing but the net flux, net mass flux through the control volume, right. That is the mass flux entering and leaving, the summation of all these things. So if you for an incompressible flow, if you remember, what was the what does the continuity equation come up to? For example, for the so if you remember, we derived the conservation of mass, conservation of momentum and energy. So in the conservation of mass, we had dou rho by dou t plus del dot rho u equal to 0, right. So this we had, but for an incompressible flow, we know what did we see, that the density this what is it? This is actually the, for an incompressible flow, the we know that the material derivative of the density is always 0. What does that mean? It means that dou rho by dou t plus u times dou rho dou x plus v times dou rho dou y plus w times dou rho dou z equal to 0, right. This is the actual definition of an incompressible flow, right, not an incompressible fluid. Remember, these are two very different things. Incompressible flow. So what does that mean? That in that flow, if we follow a certain particle, and you track its density, we will find that the density, the material derivative of that density is unchanged. What does that mean? So the material derivative comprises of this temporal part and this convective part, right. These two can individually be 0 and result in a 0 material derivative, or this can be some positive alpha value, this can be some negative alpha value, and these two can get cancelled and also result in a 0 material derivative, right. It does not mean that the rho is constant. So incompressible flow does not always mean that the density is constant, right. So we can have a spatially as well as a temporally varying density field, which can result in a incompressible flow, right. So a compressible fluid where the density can change can also result in flows where the flow behaves like an incompressible, behaves incompressibly. Okay, so is that distinction clear? It's actually very confusing at first time, but incompressibility, by incompressible flow, we generally define it as for the divergence of the velocity vector is 0, right. But this is not the correct definition of an incompressible flow. It comes from this thing, right, that the material derivative is 0. So so in the conservation of mass equation, what did we find? We found that this T plus dou by rho u by dou y rho v w equal to 0, right. And if we just break this thing, we just using the chain rule, dou rho by dou t plus u times dou rho by dou x plus v times dou rho by dou y plus w times dou rho by dou z plus the other term will be nothing but dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. And if we look at this term, this is nothing but the material derivative of the density, right, and it is 0 for an incompressible flow. So, if this goes to 0, what are we left with? Only this term, and we can just get rid of the rho term, and we are left with dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0, and in a vector form we can write it as the divergence of the velocity field is 0. Now, if we do it in a control volume integral sense, in a control volume, if we do this, we can just convert it to a surface integral. Cs u vector dv, right, and you can just do a summation over all the faces, sorry, dA, right, dA vector, it will be uf times af. So, in our case the faces are nothing but east, west, north and south, which will come out to be nothing but what the if we do the control volume integral of the divergence of the velocity vector, you will get u east, a east is nothing but delta y minus u west delta y plus, this is for the case that we are doing, right. So, u west and north delta x minus u south delta y, sorry, delta x. Okay, and for an incompressible flow, it is nothing but the Fe minus Fw plus F small n minus F small s equal to 0, right. So, you see where we get this term, we get this term from this we get this term in the AP prime, right. So, for an incompressible flow, we will get that we will see that this whole term goes to actually 0, right. So, yeah, so this is where I think we can stop the explanation. Later on we will see some other ways to get the value of the phase center values. So, what did we do? So, so in a convection diffusion problem, we the discretized equation looks something like this. So, A p prime phi p is A n b phi n b plus S u delta v. But if you look closely at the coefficients of the AE, AW, you will see that some of the coefficients like this AE and AN, let us just look at the AE part. dE minus F small e by 2. Okay. So, this term has a negative coefficient, negative sign, right. So, dE is what? Is nothing but gamma delta y by delta x. Fe is nothing but rho e delta y times UE, right, divided by 2. So here all of the terms are positive, right, because gamma is also positive, delta y and delta x has to be positive. But here if you see, the rho e and delta y can be positive, can be are positive. The UE might vary, it might be positive or negative, but in the case that it is a positive value, so if the U is greater than 0, it is a positive value, then there is a risk, of AE becoming negative, right, and this causes a problem, right. So the positive coefficients needs to be maintained for a bounded solution, right. So for a bounded solution to we need all positive coefficients. So as a result, what do we see, that there comes a sort of a condition that this should be always greater than or equal to 0. What does it mean? It means that the DE or FE by 2 should be less than DE, or we can write FE by DE should be less than equal to 2. So what does this mean? This is nothing but the cell Peclet number. So what does it tell us? It is just a ratio of the convective flux to the diffusive flux. So convective flux is written as rho E delta y by UE, and it is nothing but gamma east times delta y by delta x, right. So delta y we can just get rid of it. So we have rho E UE by times delta x by gamma east, right. This is nothing but the cell Peclet number. So we see that the cell Peclet number should be bounded by 2, or else we might run into negative coefficients, which eventually will give us unbounded and unphysical results, right. So there is a elegant method to deal with this negativity of the coefficients. We can avoid this kind of negative coefficients coming up in our discretized equations by changing the way we get the value of phi at the different phases. So in this part, sir has introduced you to the averaging method. So you average over the two cells that are shared by the phase, and in the later part we will be introduced to the upwind scheme, which will help you to avoid the negative coefficients that appear in the A east and the A north terms, because of, and also in the if the mass flux term, that FW, if it has some negative velocities in the west phase, then that might also result in a unbounded solution, because this dW plus FW by 2 might also go below 0. Why is that? Because if the FW contains the velocity at the west phase, right. So if this value goes to 0, less than 0, then this will again drive this whole term to less than 0, and this will cause some issue when we add these two terms, which again can lead to a negative coefficient, resulting in an unbounded solution, right. Okay, so I'll like to end today. So if there is any questions or doubts, you can ask me, or else we'll stop for tonight. So any questions? Okay, if not, then I'd like to end the tutorial, and I'll see you in the next week. Thank you.